You should all say that you agree.
I agree.
Yes.
Okay, we are live.
Is it streaming from the Frontiers?
Yes, you are live. Go.
Okay. Let's give one more moment. So, welcome everyone. Welcome back to our afternoon session. I would like, first of all, to thank the Pierre Auger team and especially Beatriz Garcia, who are helping us tonight. So what are we going to do? We are having an introduction to the Pierre Auger Observatory, and we are going to visit the premises of the greatest cosmic ray detection experiment in the world right now. So without further delay, I pass the baton to Dr. Beatriz Garcia, who will be our guide in tonight's adventure. Beatriz, thank you very much.
Now, thank you very much to you, Manolis and Julia and everyone here. And well, the idea is to make a visit to the Pierre Auger Observatory, which is in Argentina. For that, I will invite you to see, first of all, a very, very brief introduction about the observatory. We are here almost at the beginning of the visit, and welcome to Pierre Auger Observatory, which is a multidisciplinary project of basic and applied science. The team today is detailed in this slide. The Master of Ceremony will be Nicolas Leal, but will be with the help of Ricardo, Mariano, Marcos, Javier, Gualberto, and myself to see this amazing project. The first question I would like to ask you is about the cosmic rays. I don't know if you know what the cosmic rays are, but think in particles. They are not rays, they are not light, they are particles, very tiny particles. Nuclei with composition similar to those you can find in the solar system, or gammas or neutrinos. And the product of the interaction of the cosmic rays with the atmosphere produce a secondary particle showers. There are cosmic rays of low energy, and the main source is the sun, and the rate at the surface of Earth is very, very high, 1 per second per square centimeters. But this is low energy. At the highest energy, the sources are not the sun, can be galactic sources like supernova, and extra galactic sources, other galaxies, objects in other galaxies, and the rate, the number on the surface is very, very low, 1 per century and per square kilometer. So who is ready to wait a century to have one event associated with cosmic rays? No one. For this reason, we have a biggest observatory on the planet, and the high energy, the ultra high energy cosmic rays are part of our research. This topic in science is not very, very new, but it's not very, very old. For example, the first studies was connected with the research, the investigation by Coulomb. Coulomb is a French physicist who analyzed the discharge rate of electroscopes. They saw that some kind of process was part of the discharge of the electroscopes, but no good answer obtained at his time. more than a century after Coulomb, another scientist, Wolf, assumed that the penetrating radiation may come from Earth. And for this reason, try to make observation at different altitudes and even at the top of the Eiffel Tower. But the results were not conclusive. In 1912, Victor Hess, on board of a balloon at 5,000 meters in altitude, discovered the penetrating radiation coming from the space. And in 1932, Robert Millikan named this radiation as cosmic rays, a not very good denomination because are not rays, are particles. Victor Hess won the Nobel Prize for his discovery in 1932. In 1938, Pierre Auger, the name of the observatory is in honor of this great French scientist, installed several detectors in the Swiss Alps and discovered the shower, the cosmic shower, secondary particles produced by the interaction of the primary cosmic ray, a subatomic particle, with the particles of the atmosphere, the air molecules. The showers has an energy very, very high, 10 millions of times higher than any known before. And in 1938, Pierre Auger concluded that they were mostly protons or nuclei by charged particles. From this arrived the idea to these two guys, Jim Cronin and Alan Watson, who are the fathers of Pierre Auger's idea, and the concept of the Giant Observatory was presented in 1991, not a long time ago. In 1995 was the first meeting for the design, and in 1995 was created the international collaboration in Pierre Auger Observatory. We will describe in the next talk how the Pierre Auger works, how to detect these tiny particles who arrive out from outside the solar system, outside the galaxy, with several types of detectors. The observatory is huge, is very, very spread in the surface, and is formed, integrated by non-traditional detectors. The telescopes, we have 27 telescopes, are not optical telescopes. And the surface detectors are very special instruments. Now, 17 countries are part of Pierre Auger collaboration, more than 400 researchers, not only scientists, engineering, PhD, students, technicians, a lot of people working to make real this big observatory. More than 20 institutions on the planet are part of this amazing enterprise, which is devoted not only basic science to determine what are the cosmic rays, where they come from, why arrive to the Earth with so high energy, but also the technical development of new detectors, and also the human resource formation. For us, the students are probably the most important part of our observatory. More than 200 theses were finished connected to the Pierre Auger discoveries, and well, this is our observatory here in Argentina, South America, and in the city of Malargüe in the province of Mendoza. Since 1995, we have the first memorandum of understanding with the province of Mendoza in 1999, the inauguration of the site in 1999, the first event, the Fluorescence event in this century, and the first surface event the same year, 2001. In 2001, we detected the first hybrid event. We will know what it means. In 2005, we have the first meeting of Pierre Auger Observatory results. In 2007, the first important paper, and the full installation inauguration in 2008. And now we are here in this observatory, and I give my button to Nicolas, who is in front of the doors of the observatory in Malargüe. Hello, Nicolas.
Hello, everybody. I hope that you can see us and hear us well.
Yes, perfect.
We are here at the Pierre Auger Observatory. We will be your local guides today. And well, the idea is to show you what would you see if you were here. We would love that you can come here someday, but you will have the usual visit plus some places that you will normally not see when you are doing the normal visit. So let me show you the entrance of the observatory. Here we are at the main entrance. You can see some of the monuments that represent some of the dates, like the 20th anniversary of the observatory and some of the most remarkable events that have occurred here. Now we will enter, and you can see here all the flags of the countries that takes part of the observatory.
You can recognize your own country, probably.
Here we have
Italy
some
is
kids
there.
doing the visit and recognizing their flags. And here you can see one of the main buildings of the observatory, which is the office building. So we hope that you feel like you were here. And now we are going to enter. This is the view that you have when you arrive to the observatory. Later, we will talk about the detectors that you can see in the image. But first of all, we are going to enter to the observatory. Please let me know if the connection is okay, if you can see it correctly.
Yes, so far, yes.
Yes, very good.
Okay. So we are going to go to one of the places that you would normally not see in a daily visit. We're going up the stairs, and we are going to the CIDAS, which is the computer center. Here you can see the place where all the physicists come to take the data. And well, Marcos is going to talk about this place later. But now, if Ricardo is there, I give him the word so he can explain all the details of the observatory.
Hello, can everybody see the screen?
Yes, not a
Yes.
full screen
Yes.
for a moment. Yes, now yes.
Okay. Well, it's visible properly, or there is some
There is a
windows?
square, a gray square on the
Okay.
left, the bottom.
Okay. Okay.
Now yes, now it's perfect.
Okay. Well, it's mostly the same presentation I did some time ago.
But with the
Most
new
of-
with the new visitors, Ricardo.
Yeah, sorry. Well, anyway, I think most of people that come to the observatory will ask, well, at the end, what is cosmic rays? Beatriz already comment a little bit, and it's mostly what we say that it's very high energy cosmic ray, very high particles. In the sense that what we say about particles is not that the particle itself is a different kind of particle, but it's in principle the same particle, but with a very high kinetic energy. And if we say about those kind of particles, we would like to comment or to have an idea how big is the energy. Let us go to compare a little bit what is the energy that we talk. If we say something like 10 to 9 electron volts, the electron volts is a unit of energy that we normally use in high energy physics. Well, this kind of type of energy is around the energy of mass of the proton, for example. And if we take the highest, very high or very big accelerators that the human could produce up to today, produce for each particle around 6.5, a little bit more than 10 to 12 electron volts per beam. In that sense that the maximum energy that we can produce with all technology that we know up to now is around 10 to 12 electron volts. But for cosmic rays, we are going up to around 10 to 20 electron volts. It's a very huge energy in a single particle. If we compare this energy with the energy of a macroscopic value, it's around 16 joule. It's a very, very big energy. Well, the energy, if we compare it with daily life, it's not so big, but the amazing thing is that this energy is in a single particle, single nuclei. That's the main idea. Well, and it seems that most of the particles that we are talking is mostly atomic nuclei. Maybe not really all of them, but most of them looks to be atomic nuclei. Just to have an idea how many particles we have with that, the cosmic ray, let us say that we start with 10 to 9 electron volts and go up to 10 to 21. Well, if we see this scale here is a little bit strange, but the main division here, you will have about a factor of 10, in the sense that we have, let us say, if we have one here, here will be 10, here 100, and so on. Then having a very big range of energy means also that we will need to have a very different type of techniques to observe all of them. Then, of course, everybody wanna have a single detector to observe all of them, but it's very almost impossible to have just one technique to observe all this range. Therefore, we have some techniques to observe basically uh, the lower part of cosmic ray energies, but then intermediary or very high energies. Um, just to have an idea, we have here how many particles we have per a single um, by interval and the area that we can cover. Let us say for this region here, we have around 1 per particle per square meter per second. And if we go much higher energy, we are going to have around only 1 particle per meter square per year, or even for energies that we are interested in the observatory is around only 1 particle per kilometer square per year. And those that we are really most interested in is around only 1 per kilometer square per century. Well, at the end, how we can detect those particles? The main idea is, as it's showing in this picture here, is a single ball. Let us say that they do not have so much energy, and well, the velocity is quite small. And if we hit a single wall, it will generate some sound. And if we measure the sound that's generated in this hit, in principle, we can have an idea of the energy that we have in principle this ball. And if we start to increase the energy of this ball, at some point the ball will break the wall because the wall cannot handle all this, and then we have something like this. And if we still increase more and more and more, the what this ball can generate through this wall will be really hard to even measure the energy of this ball. Just thinking how much was the the effects that generate in this particular wall. But if we take this the secondary parts of this wall and bricks and so on, and hit a second wall here, we will may most of the particles may hit and then drop down because of the heat of the second wall. And then again, we can have an idea of how much was the energy of the primary ball. Well, if we increase more and more, the secondary bricks or parts that will hit the second wall will also may at some point start to break the second wall, and then we cannot measure again the with only 2 walls. But when we can actually put more and more walls and count the number of parts that is getting from these walls. And then that is the basic idea of how we measure very high energy particles. It's not really ball like this, but it's let us say that is a single nuclei that hit a kind of material, like a wall that I represent here. And this, in this interaction, it will generate the parts of these particles. But it's a little bit different of this model because it will not only appear a fragmentation of this material, but also new particles that is not represented here. That is a kind of effects that we can see in the when we have a very high energy particle hitting a material. Then what we apply this for, oh, sorry, I think, uh, okay. If we apply this for the very high energy cosmic ray, it will happen the same thing. We have the very high energy particle hitting the material. In our case, it will be our own atmosphere. In this interaction, it generates many particles. Those particles may have still big energy, and then it may generate other interaction, and at some point may also start to disintegrate and generate other type of particles. And those particles generated, we called secondary particles, as commented by Beatriz. Well, at some point, those particles will have low low energy to be completely absorbed by the material. Then at some point it will, for us, like it will disappear, but it's not really disappear. It will be somehow absorbed by the material and then disintegrate or whatever. But then the idea is mostly like what we have here. And then the idea, what we have is those particles are normally can generate ionization, excitation in the material, because most of them are charged particles. Can generate also light by effect of Cherenkov. That is a type of effect with very high energy particles hitting the material, but also can generate fluorescence or some other effects. Also can generate radio waves. Then the main way we are detecting these particles are basically trying to identify this ionization, these lights, or radio wave. That is the main way we are going to detect this cause. Well, the shower that somehow we are detecting the primary particle that we have here. In this shower, we have many types of particles. Some of them can travel very big amount of material. Some others will interact promptly and then mostly can be absorbed. Then in this type of shower, we may try to use different way to try to understand which particles we are really seeing in some particular point. Sorry. Okay. The observatory has been designed to be to observe mainly cosmic rays above 10 to 19 electron volts. As the flux of these particles is very low, we will need to cover a very big region. That is, we are covering around 3,000 kilometers square. And that is comparing with city of Buenos Aires is around 15 times more, 15 times the area of capital of Argentina, for example. We are using two different techniques, and that is we called particle detection, that we called surface detector, and another type of detection by fluorescence, looking the fluorescence light generated by the shower. And this is what I say international collaboration that really build out this facility. Well, here we have an idea of what we have in the as a surface detector. It red dot here is what we call one surface detector station, and beside that we have 4 points where we have fluorescence detectors that we are talk a little more in detail later. Well, the fluorescence detector, basically the idea is we have the particles in the shower that interact with nitrogen in the atmosphere, and this interaction generate excited nitrogen molecules. And these molecules, excited molecules, can go back to the normal state, and when it does, sometimes it generates also light that is propagated isotropically from the fluorescence from the shower of particles that we have. And this light can be observed by telescope that is quite far away from this where it's generated these showers. the telescope that we have in the fluorescence detector. I think Mariano will comment a little more in detail about that. And then I am not going to explain much more. And the fluorescence detector, or surface detector, I mean, is particles detector that is suppose that it is, oh, sorry. Okay, this line here represents one each particle of the shower that hit the ground. And some of the particles can really travel through the tank. While it's traveling through the tank, may generate the light by Cherenkov effect. And this light, some part of that will hit the very sensitive light detector in sitting on top of the tank. Basically, the tank is composed of purified water that is and the 3 photomultiplier tubes that is these very sensitive light detectors. But to keep all these working, we need to have a power supply and the batteries to keep the electronics that we have here, and also make the communication and synchronized with all the other detectors, surface detectors that we have installed. Well, nowadays we are making a kind of a upgrade of this system. Then what we have basically is this is the normal tank that we have already working. And beside that, we are installing what we call the Amiga, that is scintillator, another type of scintillator that is sitting on top of the tank, and also one antenna that is going to observe the shower by looking the radio waves generated by this shower. The idea is those particles that are traveling that having in this shower, that is, let us say this particle here is 1 muon, for example. Muon are normally particles that can travel a lot in the material, while the other parts, some other particles may be really absorbed or have a big interaction with material, and then most of the time is absorbed in the first layer, let us say. And then the idea of this scintillator on top of the tank is basically to observe all the particles, while the tank, as it see a little bit different way, it's going to be able to somehow discriminate the amount of muon comparing with the electromagnetic component that we called electron, positron, or whatever. Beside that, Amiga is almost similar to this, but instead of make the detection of both, is mostly try to put really under the ground, in the sense that many particles that have a big interaction with material is really absorbed by the ground, and then some of them, most of the particles that penetrate a lot in the material can be really observed by this scintillator that we call the Amiga. That is the idea that we have installed in this position here, and then we can observe different aspects of the shower in the sense that we can, in principle, can understand better what is really the first interaction, in the sense that also we can understand better what is the particle that really hit in the top of the atmosphere. I think that's all. It's mostly a summary of what we have. In the fluorescence detector, we have basically 4 buildings, since 6 telescopes in each building, and each telescope has 440 photomultiplier tubes that are the very sensitive light detectors in each telescope. The fluorescence surface detector is composed for 3 photomultiplier tubes for each tank, 1,600 tanks with very purified water. Each tank is 12 1,000 liters of water, purified water, and it is disposed in a triangle grid with 1,000 kilometers and 500 kilometer, 500 meters space between them. And nowadays we are making this upgrade that is adding mostly three type of sorry. Oh, three type of detectors and new electronics, and we would have a better resolution in the sense that we would be able to be more sensitive to the composition of the particles. I think that's all what I have.
Great, Ricardo.
Yeah. Well, I don't know. Well,
can we ask
Now,
questions now, or we do it in the end? What
well,
do you
if you
prefer?
have questions, we are waiting for the next talk. So if you have questions, I think you can make it now.
Okay, so there are two questions actually. The first one is that the particles that you observe are mainly muons, right? I mean, the end particles that you observe in the detector are muons. Are we correct? And also from Panagiotis, we have the question that in the sketch he sees electrons and positrons. Do you observe any anti-muons?
Well, when we say muons in general, it's we cannot distinguish if they are muon or anti-muon. Okay, it's and we are not that sensitive to really distinguish between them. To say that we are detecting more muons than others may be true, but I think we are really detecting most electromagnetic component that is positron and electrons. Well, the way we are sensitive to those particles is different for each particle. Then it's really hard to say which type of particles we are really detecting, at least in the tank. When we talk about the Amiga detector, as it is under the ground, most of the particles that they are detecting are muons, because electromagnetic components are mostly absorbed by the first layer of the ground.
Okay, thank you very much.
You're welcome. Some other question?
There is, I have one more question. We are also waiting to see if we have something in the chat or Facebook. But the question is, you observe the particles, so you can say that the shower happened or didn't happen. What about the energy of the shower?
The energy of the particles that get into the tank, or the
of the shower,
primary?
of the shower itself. I mean, can you estimate the energy of the shower with this experiment?
Yes. Well, the energy of this particle here in the primary one, we estimate by looking the amount of particle, or how big is the spread of this particle around the ground. If we put one detector, let us say near close to the edge of this picture here, it's going to have a very low number of particles observed. If we move close to the main region here, it's going to be a very big amount of particles. And then looking at the distribution of these particles on the surface here, we have an idea how big is the energy of this the primary particle. This is the technique looking the surface detector. Looking the fluorescence detector is a little bit different. The amount of light produced in the while it's propagating depend on the number of particles of the shower that propagate through the atmosphere. And then looking the intensity of the light that we receive from each direction, we can estimate how many particles we have in this shower. And having this idea, we can also estimate the energy of a primary particle.
Thank you very much.
You can.
Just waiting for, oops, sorry, just waiting for Mariano, I think exposition,
Yes,
presentation.
I'm here.
Give me a minute just to show one slide, just one slide, connected to the secondary particles in the atmosphere. Look at this. Here you have a shower, 3 kinds of showers, iron, protons, and gamma. When we said iron, we are talking about nuclei. And as you can see, we have a lot of secondary particles. You have electromagnetic particles, light, not visible, but light, muons, these high mass particles, more massive than the electron. And you can discriminate which kind of particles are in the shower because you receive different signals in the detectors. So it's possible to discriminate the particles, it's possible to reconstruct the direction of arrival, and it's possible to have the energy of the primary particles. The problem is discriminate the mass, You determine the energy, the arrival direction, the secondary particle that you have, but the mass of the primary is one of the answers which Pierre Auger wants to answer. So it's part of the discovery. But you can reproduce this shower theoretically, as in this slide. Okay, let's go, Mariano.
Okay, hello everyone. Can you hear me?
Yeah.
Good. So I will share something here. And can you see full screen?
Yes, perfect.
Yes.
Okay, good. So here we go. So when Ricardo was talking about the fluorescence detectors, he was talking about this, what you see in the screen. It's a big building. It's an electromechanical building composed by 6 bays. That, okay, Ricardo already explained the information about the physical part of the fluorescence phenomenon. Mostly we use this building during clear nights just to observe this fluorescence phenomenon. And during the summertime is more or less, we use it for 14 nights, 8 hours each night. And for winter, we have something like 20 nights, 14 hours each night. The building, as you saw in the previous image, we have 4 of them placed at the side of the detection array. I will show you later. And is remotely operated. At the very beginning, it was operated by the scientist's own place. So you have a kitchen, bathroom, and you have everything there. But later we move it to the CIDA's place, which is the acquisition room, where all the data is transmitted from this tower to the main installation where Nicolas and the rest of the people are at this moment. The first remote station was implemented there in the CIDA's room, but now we have plenty of the remote station, for example, in Italy, France, Mexico. Okay, there are a lot of stations, something like 14 or 17 stations. And as I say, we have 4 of these telescopes. If you see the people, I want to have an image of the people inside the building because I will show you some other images later, just to have an idea how extended is the size of this. Okay, here you have the image. So the same the building is the small one that you see there. You see the tower. And as you can see in front of this, you have plain land. And of course, you are not going to see the tanks in front of the telescope. You can see something there, just to have an idea how extended is the place of this detection array. During the night, we can have something like this image. And if you go in front of one bay, you are going to see, okay, you see the size of the person there in front of the telescope, and you can see the UV filter plus 2 doors that we call shutters, just to have an idea how big it is. And inside you have, as I said, 6 bays composed by, this is more or less like it's not a perfect semi-equal, but it looks like a human eye, because you have a mirror that sends the light coming through the UV filter to the camera. The camera send the camera is composed by 440 photomultiplier, which are sensor of light, and send the signals to some electronics. And finally, the electronics takes a few decisions about which light is important for us or not. And it filters in some way and translate the analogic signals to send it to some computer, doing the translation from analogic to digital. And finally, send everything to another main computer, which is the brain computer or the eye computer. So in order to protect the camera against any kind of light, we have curtains and some shutters that you already saw in the previous image. Regarding to the schema or the networking for the computers, if you saw in the previous image, you saw the camera with the 440 PMTs, the electronics that do the translation, the computer that take the signals and send it to the main computer, which is the eye computer, and finally sent to the communication antenna. Of course, each unit, also for the ST station, have GPS unit to do the recognition of the event on the place and distance in the ground. You already saw this when I was talking about the building in the outside of the detection array. I was talking about this. So this is how the buildings are pointing to the field. And also in the field, we have different lasers. I consider it important to put the laser because in some way we need to know the quality of the atmosphere. Again, you can see some images to have an idea of the size of this. And with the laser, we scan the atmosphere for aerosols and so on. Okay, I don't need to explain. What the electronics do is a kind of filter in some way to recognize activation for individual pixels, then some kind of second trigger, which is a line of patterns. There are much more complication than this, but I wanted to show you this because it's quite important. And finally, by software, we do some recognition of the timing on how is activated all those pixels. Regarding to the procedure to take data, even if it's locally or remote done, we need to follow some schedule that it will tell us how to operate the telescope according to the moonlight and also the sunlight. By moving the or by closing and opening the shutters in order to protect the camera. So for example, for one of the building, we have the 6 telescope, and we know that at some point we need to open all the bays except number 6. At some point of the night, we need to open that number 6. Then we have another schedule to shoot some lasers. So we need to close a camera just for avoiding getting flood of events. And okay, so the people that usually the students that execute the procedure, they need to arrive 2 hours early in order to do some another test, like testing the equipment, electronics, and to warm up the electronics in order to do some calibration. We need to do some calibration at the beginning and at the end to know how it behaves, the photomultipliers during the acquisition. We have a kind of reference in some way. During the acquisition, we have, okay, we need to operate the telescopes as we saw in the previous image. And then we need to check the behavior. Marcos later will show you the room where he is now. And you are going to see these screens. And if you see the screens representing each building, inside, in detail, you are going to see the information for electronics variables that will indicate us how it's taking data. Again, the triggers or the filter, how it's working, if it's arriving event or not. Some information about the rate of event that we are getting, and information from sensors placed in the building regarding to wind speed, rain, temperature inside the base, position of the telescope, position for telescope in another case, but in this case is shutter and curtains. Information about the lasers when they are shooting the GPS signature in order to check that is right, and some activities performed during the night. So more or less, this is what you are going to have in the main room. But of course, there are many tools that we are using to know how it's outside, because remember that you are far away from the telescope. So you need to use a lot of devices to realize how is the sky during the night. For example, if you see in the image down there, you have the different telescopes and you are seeing the Milky Way there with another camera. One thing is to operate the telescope, and finally, you need to know what you are taking or what you are receiving. We have separated time for do that. During the acquisition, since we need to see events really fast, we use some kind of online display that is only showing you the 440 photomultipliers on each camera with the GPS second signature. But when you mark the pixels, you want to see the signal on time, on a window time. But of course, if you want to see more details, you need to wait a lot of other variables to be collected with the purpose of seeing the energy, direction, geometrical reconstruction. In this case, I'm showing you an hybrid reconstruction where you see 3 different buildings plus some SD stations. So by joining all this system, you can have more resolution of the events. And what you are seeing there, you are seeing the shower, the profile of the shower. In some way, what you are seeing is how the particles interact in the atmosphere. For example, here you are seeing how increase the interaction to some maximum point of energy that it fits with the image up there. Oh, sorry, I click it. And at some point it starts decreasing the interaction and we lose the camera because the event probably continue, but we don't have more camera. So if the event happened far away, probably you are going to see the full trace of the profile. Regarding to the procedure, of course, we have, while we are using the detectors, some issues happen sometimes. We have different maintenance tasks. One is for regular preventive maintenance, which we are doing regularly, like testing the computer, devices, shutter curtains, electronics, and so on. But the most important is also the corrective maintenance, which we need to solve it immediately, daily, in order to keep the detector working as much as it can, because as you saw at the beginning, we have short time to do it. And that's all from my side. I hope you understand it.
Thank you very much.
You're welcome.
Yes, very good. Very good, Mariano. I believe Nicolas will show you a little more of CITAS, of the Computer Center in Pierre Auger. It's right.
Mariano should, sorry, Marcos should be there.
Okay, Marcos, hello. Marcos, are you there? Well. Meanwhile, I would like to say, are you there? More or less, Marcos. Oh, now yes.
Okay, I will take his turn. Let me.
No, it's okay. Now we can see.
Just a minute.
Yeah, okay. If you will take some time, I would like to say a little thing, can I? It's just to put our mind again in the astronomy problem, if you permit me, because I'm not a physicist, I am an astronomer, and I don't know if the professors here know that, but the astronomers all the time we are thinking in our main object of study, which is the light, but the idea is this one, please. It's good for the professors and teachers because at the classroom, we all the time are talking about the astronomy in general, and the astronomy is everything. It means the astronomy is the discipline which study the celestial objects, but also the properties of the universe, all the properties, and study the time and the space, and study everything that exists right now, and will exist. So, in general, the knowledge of the cosmos is through the photons, through the light. And in this sense, we know what is the light, the different regions of energy, what our eyes can see, and what energy is outside the region or the visible region. But the idea is that we produce technology to observe this light and to extend our vision of the universe. Remember that at the beginning, 400 years ago, the telescopes were not part of the technology for the astronomers. Now we have telescopes to see to the past, but using as object of study the photons. So we can go far in time because we have telescopes. But if we present the image of the universe in this very, very well-known image, we have a big period of time who can be studied using telescopes, using different kind of telescope, because the telescope study the light. It's the yellow region. This yellow rectangle is the time in which the telescopes are usable and very useful. But at the first years of the universe, the matter and the energy were accouplated, were united. So it is impossible to see this time. It's impossible to see the first 400,000 years of the universe. But we can change a little our mind and try to study the particles, because the particles interact each other, interact with the matter, and we can observe the secondarism. It means we can observe the interaction, because the interaction is in the format of light. When we had, as we had a limit with telescope, we invented Another technology, probably you visit some of these observatories, this specific center of research, in which there are accelerators. The accelerators permit to reproduce energy conditions, the first moments of the universe conditions, and then if you change the scale, and now the yellow region, the region observed with telescope is marked by this yellow rectangle, you can see that there is the first years of the universe, the first instant, the first seconds of the universe, which can be studied using accelerators. Probably you know the Fermi Lab or the CERN in Geneva, and you visit the great or the Large Hadronic Collider, also there in Geneva, France, space. But you can know also detectors on Earth to detect particles who arrive from the universe. For example, neutrinos. This is an observatory of neutrinos, the Super Kamiokande, a very, very famous instrument to detect neutrinos. Here is another vision of the Super Kamiokande with photomultipliers tubes to detect the interaction of the neutrinos with the water. Here, there is a boat, water, the interaction produces light, as in Pierre Auger surface detectors. But also we have instruments installed in the Antarctica. Here is the ice cube to detect neutrinos interacting with the ice. But all these particles are part of the high energy universe, the universe called extreme universe. For example, the supernova, for example, the pulsars, neutron stars, and so on. So to study the highest energy in the universe, we just have one object of study, and are the ultra high energy cosmic rays. For this reason, this observatory is important, because it's the only way to study the highest energy in the universe. And that is all from my side. And now I hope to be at the CIDAS.
Hi, can you hear me?
Perfect.
Okay. Okay, I am going to show you some of the one of the maps we use during the introduction in the FD. Much of the information that Mariano said was all here in the CIDAS. Okay, CIDAS means Central Data Acquisition System, which is mainly this room and the server room. Okay, I wanted to show you this map, which is just a map that you might know, but at the center you can see the both lasers facilities, and around the array you can see the FD buildings. Okay, we are here the campus in Malargüe, and I wanted to show you this because we can understand the data flow of the information here by just knowing that every surface detector is connected through a 900 megahertz link to one of the 4 buildings. Okay, so the complete array is divided by 4. Okay, and then between buildings we have a microwave link, and we are happy to say that nowadays we have a redundant link where we can connect not only through the normal way from Loma Amarilla to Curhueco and then to CIDAS here to Malargüe, but also if we have a power cut or some communication problem, we can connect through, for example, Loma Amarilla and Los Morados and Los Leones. So this is new. In the last month, we can reach that link. So we are happy to say that. And all this information coming here through the microwave link is coming to the CIDAS server room, which is there. Mainly it's air-conditioned room, because this room has all the service we need for reconstruction of the events. Okay.
Can I say one thing about the array of tanks? Because you mentioned that the communications were through the microwave link, but I would like to say that all this surface that you see, each point is a tank, a surface detector, and the provision of energy is solar. All is with a photovoltaic system. It's the biggest photovoltaic system for a research institution. Each tank has its own photovoltaic system, and is all managed with the solar power and, of course, batteries. You will see the tank outside in a few minutes.
Yes. Okay, in this part, we can see as Mariano mentioned, all the monitoring screens. We have some screen here with the current data, where, as Mariano says, we can monitor the parameters, not only light or variance of during the night, but we can also check the shutter, and we can check also the lasers. We have information about calibration and about the wind speed and rain. All the main information we need during the night, during the shift, is here. In this computer, I will show you that we have all the information here about the data. This is current data, okay? And I wanted to show you here that we are seeing here a data, but we can point one of the pixels, some of the pixels here, and we have this plot here. Over this plot, we can get not only information about the signal strength, but also about the timing, which is important, because we can think that this event is completely vertical, but by getting this information about timing, we can really know that it's not exactly vertical, okay? And also we have some information about timing, where all the reconstruction software can join the information of all the buildings and the SD detector. And after that, have information about the hybrid events, okay? Not only FD, but also SD. And that's why I wanted to show you here. This is the event display showing not only here, not only the SD, but also the FD, okay? We have a list of events where we can try to get an image of the events during the night, okay? Here we can see this is an example. We can see this part of the right, but also the buildings, 4 buildings, Mariano mentioned. So with this tool, we can, during the night, we can check that everything is running. And if we want to try to figure out what's happening with the events, we can check this information. Okay, I think this is the main information about the CIDAS. And as Mariana mentioned, we have all kind of tools and parameters to check during the night. Okay, so I think this is all we had to check here. If we want, we can move to the office building. Okay.
Yes, please. Remember that this area is not part of the regular visit. It's a private section of the building. Is where the offices are. You can see there the offices of the different groups. Okay, let's go to the right. To the right, you will see the stay room, and
we are moving to the conference room, to the meeting room, and we can see one special detector here.
Yes, you will see from the window, no? Through the window,
yes.
the detector there. We will visit it in a few minutes, but it's good to see the detector from the first floor. You see
Yes.
the surface detector on the right, and on the left is AERA. Is one of the new kind of detection you will hear about AERA in some minutes. And there, the flags entrance and all the park.
The park. Okay, now we are going to move to the assembly building to check all the Amiga facilities and the SSD.
Okay.
This is also not the regular part
of the
okay?
visit. Yes.
Yes.
And you will go walking, or Nicolas is there? It's just there.
No, I am here. We will need to walk.
Yes.
Okay.
We
This
have
is,
problem with the Wi-Fi,
yeah.
so
okay.
that's why we're doing the.
No, don't
with one
worry. It's
cell
good
phone.
to see all the building. Now
Yes.
it's the interface between the office building and the assembly building, which was one of the first buildings constructed here in this site, because there were assembly all the surface detectors. So now is devoted to the assembly of Amiga detector, but in the past, this space was full of surface detectors, tanks. Okay.
Okay, as Beatriz mentioned, this is the assembly building of the observatory. Here was the place where all the tanks were assembled. And now you can see all the upgrade projects being built here. Here you will see all the mechanical aspects of the observatory, the assembly of the different detectors, and also how do we manage to deploy these detectors in the field, which is a very challenging task because of the conditions of the ground and all the different terrains that we need to sort out in order to deploy these detectors. So I'm going to start with the Amiga project. Here you can see two of the Amiga detectors. Each detector measures 9 meters long, 1.4 meters wide, and it has a very small thickness of a very few millimeters. So it's a very thin detector. That's why it's very difficult to move, to handle, and to move to the field. I'm going to enter to the assembly room of the Amiga project. Here we have two detectors, and the idea is to build 210 detectors in order to equip approximately 70 surface detectors with the Amiga detectors. As Ricardo mentioned earlier, the Amiga detector is 2.5 meters underground in order to measure only the muonic component of the secondary shower, because we use the ground above the detector to filter the electromagnetic components. The detector inside is composed by scintillators. The scintillator is a plastic extruded bar. I don't know if you can see it. This is a cut of the scintillator. Yeah. The scintillator measures 4 centimeters wide, 1 centimeter of height, and it has a cover of titanium dioxide. And inside the scintillator, we have an optical fiber. Yes, and this optical fiber.
Can you put your finger near the?
Yes.
Yes, yes, because it's in this way we can understand the dimensions. Yes.
Yes, I don't know if the scale is correct.
Yeah, it's perfect.
This is the scintillator, and the Amiga detector has 64 of these scintillator bars. We have 64 bars of 4 meters of length. We have 32 of each side of the detector. And all those 64 scintillators with the fiber inside and glued inside are connected to a collector of light that we call the cookie, which is this device here, where you can see all the endings of the optical fibers. Yes, this surface is very polished in order to make a good coupling with the electronics that sense the light. I'm going to show you the back of the cookie. You can see all the fibers that are routed from the scintillators through the cookie. We build these detectors of Amigas from the ground. I mean, we have all the materials to build the detectors here. The material is PVC, and we have a lot of PVC here. And we cut the PVC, we fold it, and we glue the scintillators on top of each plastic covering. Yes. And finally, here in the optical coupling, we placed the electronic. This is an electronic which has an FPGA and a silicon PM in the lower part. We'll show it here. So there you can see the 64 silicon PMs, or silicon photomultipliers, and each one of them is optically connected to the end of each one of the fibers. So we can know exactly on which scintillator the muon hits the ground. And in order to transport such a big detector, we use this vacuum holder, which measures 10 meters long, and we use the vacuum created to suctionate the detector and move it to the field. So it's a very delicate task, because we are talking about optical fibers that cannot be bent or hit. So we have to be very gentle with the handling of these detectors. Okay, so I'm going to move to the next project. I don't know if I can answer some question here of the things that you saw.
Well, one of the questions is if the entire production of the detectors take place on site. In part, you answered that.
Yes, previously the detectors were assembled at Buenos Aires, Argentinian capital. But right now we have all the components here to build them from the ground, from the.
Falling asleep. I'm not listening.
When the detectors were built on Buenos Aires, it was a very difficult task to transport the detectors from Buenos Aires to Malargüe, which are like 1,000 kilometers, and then to the field. We had a lot of chances of breaking some of the optical fibers inside the detector.
Yes, I didn't mention it, but in Argentina, there are several groups working in Pierre Auger in general. And one of these is in Buenos Aires. Remember that Pierre Auger in Argentina is managed by the Commission of Atomic Energy, the CONICET, the province of Mendoza, and the Malargüe city. But mainly the Commission of Atomic Energy, which has a part of non-nuclear activities, but high energy activities and research. So in Buenos Aires, there is a group in Bariloche, in the Atomic Center in Bariloche, there is another, and of course in Mendoza and in Malargüe. So several groups, several universities, including the National Technological University in Mendoza and Buenos Aires and San Rafael, 3 cities in which the Technological University has faculties, are part of the project.
Okay, now I am here at the SSD project. SSD stands for Surface Scintillator Detector. So this is the detector that goes on top of the tank on the scheme that Ricardo showed earlier. Sorry. This detector is pre-assembled here. The detector arrives to Argentina from 6 different locations, mainly at Europe. And we receive the detector, as you can see it in this table. We receive the detectors in a container, in a pallet, like that, all piled up. And the task that the technicians need to do here is to put the aluminum roof on the top, like this. This is a detector that has the aluminum. And also they need to put all the components that makes the coupling between the optical fibers and the PMT. The scintillator works just like Amiga. You have some scintillators that have some grooves where the optical fiber can go through. This is one of the difference between Amiga and SSD. The optical fibers in the SSD goes through the scintillator. I don't know if you can see it there. The scintillator has a hole, and the fibers go through the hole. The Amiga scintillators, the scintillator has a groove on the top, and the fiber is glued. So this is like a cut of the detector. And you can see that it has some foam on top and bottom in order to make the isolation of the scintillators. And also it has an aluminum covering all the perimeter of the detector in order to be sealed of light. So the light cannot enter to the detector. So as you can see a place, this is closed now, but here is the place where you can unscrew the top and put the PMT to sense all the light that is collected from the optical fibers. This project will be placed in approximately 15,100 detectors. So we have 1,600 surface detectors, and we will be covering almost all of them with this project. And also, like Amiga, it is a very challenging task to deploy these detectors. It's a very much faster deployment. The technicians can deploy 6 detectors per day. One team is deploying 6 detectors, and other team is here assembling 6 of them in order to be deployed the next day. Okay, I don't know if you have any doubts. If not, we can go outside and see
Yes,
a whole detector with all the projects installed. Here you can see the south part of the observatory. And now we will go to a fully equipped tank.
For the people who don't know, Malargüe was chosen as the place to install Pierre Auger because the weather, the clear skies, the altitude, and because we needed a very huge area at the altitude. So it's not so easy to find 3,000 square kilometers at 1,400 meters above sea level. So Malargüe was part of a search of sites for Pierre Auger. In Argentina, Argentina competed with other 2 countries, South Africa and Australia. And in Argentina, we offered 3 sites. And finally, we chose, because was the best of the 3 sites, Malargüe. It was a long process to select the site to install Pierre Auger. Okay, let's go.
Okay, here we can see one fully assembled new detector, which is not only the SD that you know, okay, the one you Beatriz mentioned, but also, can you hear me?
Yeah, perfect.
Okay, but also in the middle you can see the SSD detector, okay, and on top you can see the RD, the radio detector. One of the upgrades that we made to the detector is the solar panel here, which is now we had to install this 200 watts solar panel, okay, and after removing the 50 watts, all the solar panels, okay. And so I like to see this detector because this has all the new detectors of the upgrade, okay. It's not only SD, but also the SSD and the radio detector. And the radio detector, which is on top, you can see that there are 2 metallic rounds, which is the antenna, okay, which has 2 polarization, the north-south and the east-west polarization, and it's composed of low noise amplifier on top, okay, and then it's connected to a new front end, which we call a digitizer, but it's only a front end, okay. This new digitizer is connected to the UUV, the new UUV, which is also an upgrade, okay, that it need to be installed. So this is all the new parts of the detector that we need to install. The plan is to install at least 4 of these RDs, which is mainly the metallic structure and the antenna, and also the digitizer. Hopefully, in the same time, we install the solar panel. Okay, but the idea is to install 4 of these sets per team. Okay, per day. So I think this is all about this new detector. I think we can move to Aera. I don't know if you have question about the full detector. Okay. Okay, we are moving to the Aera that Beatriz mentioned earlier and Enrique Gaviola see. As you can see, in the fully assembled detector, we have 2 metallic rounds, which is the Sala antenna. But here in Aera, nowadays, we have 124 detectors that compound this Aera array, which is a butterfly-shaped antenna with also 2 polarizations, north-south and east-west. And we have a 140 watts panel. Okay, and here we had a metallic box that we needed this metallic box because the radio detection has this all the electronic noise from outside, from digitizer or switching power supply, everything that is emitting some signal might interfere with the radio detection. To have an idea, the radio detection is made between 10 and 90 megahertz. And as you can imagine, we have the FM stations, okay? So, and all the new switching power supplies, all the noise might be in that bandwidth. So we need to shield everything to avoid having this noise inside. That's why it was a very tough task to perform, that to shield and to remove this noise from the detection. So the Aera group has to modify some part of the UUV, the new UUV, the detectors, the electronics. Okay, had to modify this in order to remove this noise. So, but nowadays we can say that it's a very promising mixture of detectors that we have in the new upgrade detector. This one is the one we show previously, which is Enrique Gaviola detector, and we can see here the old. I want to know this is an old, but this is the solar panel we have installed in the full array nowadays. We only have 10 of the new Luxor solar panels, which are much bigger, but we have to install all of them in the near future. So this is the array, and you can see here Here is where we have the electronics, okay? And the full compound is the solar system connected to 2 batteries and a regulator in the battery box. And then here we can get access to the electronics and the connection to the Yagi comms antenna, which is the 900 megahertz link. Okay, and this is mainly that what you have in the field nowadays. Here you can see the battery box. This is where we have the batteries and the regulator.
You mentioned the name of the tank. This tank has the name of a scientist, an Argentinian scientist, Enrique Gaviola, but each tank has its own name. And at the beginning of the observatory, the names were selected for the students in primary schools mainly, who were invited to name the tanks. For this reason, each tank has a name, and the most part of the names were chosen by the children from Malargüe. Was part of our citizen science project with Pierre Auger. Oh, now you are. Oh, okay. Now you are fine.
Can I ask one question?
Yes, of course.
So why do you need to go to 1400 meters altitude?
Well, if you remember the shower, let me show you something. Wait a minute. If you remember the shower in general, as now you will see the image at the screen.
Yes.
When the primary particle hit the atmosphere, you produce the particle transform the energy into new particles with new energy. So the process of production of secondary particles started. But there are a maximum altitude for which you have different path for the particles and not a big confusion of the particles. If you continue, the particles will interact one each other, and you will have the addition of the particles produced on the ground at the surface, and the confusion is so high that you cannot discriminate between particles. There are primary is a model, but now is experimental result. You have the possibility to study the complete production, the complete deployment of the shower between 800 and 1,400 meters above sea level. If you are so high, the shower is not open enough, and if you are so near the sea level, the number of particles is not the particles produced by the primary one enough and alone. So you need this condition to select the site to install the observatory. The altitude is one of these. You need the full coverage and the full aperture of the shower, which is deployed as a cone through the atmosphere, to have the certainty that the results are connected to the secondary particles produced by the primary cosmic ray.
Thank you. And there is also one more question from Facebook, which is called, which is the shelf-life of the detectors? I'm not sure. Shelf-life, I'm not so sure what it means. I suppose how long they stay, they need without operation, maybe?
Maybe. Well, as almost all the projects on the planet, The estimation for the life of the project is 20 years. But we started in the past century, in the last century, in 2020. So in the 20th century. So we are working for more than 20 years. But when the 20 years arrive, we extend the useful life of the observatory with a big meeting, a very, very important party to extend the useful life of the observatory for 20 more years. So we are in the second life of the observatory with all the surface detectors installed and with the new detectors which are being installed in the future 20 years. So, well, we are working for a long time and we hope to work for more because each project produces new projects, new things. The technology change with the time. So we are producing also, we are replacing old technology and install new one as the solar panels or the photomultipliers tubes. We are changing the technology because the technology changed more or less each 5 years completely. So we are part of the plan of the observatory is the update of the technology, the update of the detectors, the update of the projects, and the installation of new projects, which also are part of the new groups, new countries, new institutions, more students, more scientists, more technicians. So each big project, each collaboration produces more science, not only the science for the first objectives are each year are more and new ones. Okay, I don't know if there is another question, and is if no, you are welcome, Manolis. And the people are in front of the building, I think, again.
Yes, we are here in the visitor center.
Fine, great,
So
let's go.
we're going to enter it. Here you can see a nice, like a simulation of a shower in the door. And now you will see what all the visitors of the observatory can see. Here we have a list with all.
You have a problem with the Wi-Fi,
from 19.
Nicolas? Nicolas? Well, Nicolas is showing the timeline. I think you have some problems with the connection, Nicolas.
Can you hear me now?
Yes, now, yes, yes.
Okay. So I was showing this timeline with all the discoveries that Beatriz talked before. And I want to show you some of the mechanical parts of the observatory, like this. You can see here only a quarter of a mirror of each telescope. So you can see if Marcos stands near the mirror in order to make the scale of how tall is a full mirror.
The full mirror, remember, is almost 4 meters by 4 meters. This is a quarter.
Yes,
and the mirror is not a unique piece. It's constructed by small pieces, as you can see. It's like a puzzle. You can produce an image as a unique mirror. and the mirrors are fixed, not moving as normal telescopes.
So here you can see the photomultipliers that we use at the FD telescopes. Those are very small compared to the surface detector photomultipliers. So
Which
we have
you
this,
have one near, right?
Yes, I'm going to show the, well, you saw the picture of the building. Here you have a representation of the mirror with the camera on each telescope. This is what Marcos told you before. The UB, or the universal board, is the electronics of the full detector. Here's where all the projects are connected. Here are the parts of the surface detector. First, in the inside, we have a bag, a bag filled with the ultra pure water. And here, this is an scaled version. Here you can see that the bag has 3 windows. Those windows are the places where the photomultiplier is placed, and the photomultiplier is looking into the water. So you can see the full size of the photomultiplier. And here a small version of the surface detector. And this is like a general view of the visitor centers with all the positions that the people can come here and see and touch and hear and learn whatever is their interest, because you can guide yourself and navigate through all the contents of the observatory.
Okay.
Can I ask one question?
Yes.
Yes.
You said that your stations are fully autonomous with solar panels and so on, right? But the photomultipliers need something like 1,000 volts or more to be in operating voltage. So this is quite some energy. This means that you will need lots of solar panels, let's say. Am I correct? Okay.
Each tank has its own solar panel and a full photovoltaic system. Each tank. In this sense, we have 1,660 solar panels, and now a bit more, more power because more detectors. So we have more detectors. So yes, if you put all together, we have an amazing amount of energy to make the observatory reality. Yeah.
And what happens?
Yes, it's true
what
that
happens if it's cloudy?
Well, we have some prevision for bad weather, but when you have, for example, 1 week without sun, which can be possible, we needed sometimes to stop the function of the observatory because the surface detector are functioning 24 hours a day. The fluorescence detectors are not powered by solar panels. They are connected to the line, the electric line, because the surface detector needs a lot of energy. But the tanks can be that you cannot have enough energy storage in the batteries, and sometimes we need to stop the functioning of the observatory. But it's not a normal thing because Mendoza is a province with a good quantity of clear days a year.
Just a comment. I think that there is a little bit confusion. You said about high voltage, right?
Yeah.
Well, the high voltage is produced by by a power of 12 volts. And then there is a small device that
Regulate, yes,
elevator arm
change.
multiply this voltage to up to close to 2000 or 1000. Then it's directly the power from the battery that we take another device to get up to close to 1000 volt. But
Yes,
as
but
the current,
this needs to be powered somehow, right?
yeah, but it's directly from the battery power. Batteries
I
that
see.
is taken from the solar panel also.
Yeah, for the
And
batteries.
there
yes,
is no
that's right.
need to have a big amount of solar panels for each station.
Yes.
Yeah,
If you can see here, you have
Marcos.
the high voltage converter that switch from the low voltage from the batteries to the high voltage needed from the PMT.
Yes, this small box that looks to be aluminum box is the high voltage power supply, let us say. It takes from 12 volt and then convert to up to close to 2000 volt.
Thank you very much.
Okay, well, I think this is the end of the visit. There is a Geiger counter. There is a Geiger. I don't know if it is functioning and if we can hear. This is a detector of cosmic ray in real time. It's a Geiger counter. And you can see two tubes which are full of gas. And when the particles cross the tubes, interact with the gas, the electrons are free, and a cable collects the electrons and produce a signal. And you can hear the pass of the particle, and also you can see the counts there in the display, the LED display. It's possible to hear the Geiger count?
I don't know if this one
is.
Oh, yeah.
These are cosmic rays in real time. You can have the signal, you can see the number in the LED display, but also you can hear. And you have different frequency for each tube. And when you hear the shower, you hear two frequencies at the same time. And you hear? And you have coincidence. And this is the way in which Pierre Auger works, by coincidence between several tanks to determine that you have a shower and not an event, an isolated event, no, a shower. The coincidence between several tanks produce our data. We need coincidence, and we have a lot of time to assure that several tanks detect the same thing. For example, this is another model to see that. The event produced that each tank detects something, but if you have only one tank, it's not a shower. The shower is produced when the secondary particles shower arrive to the Earth with different tilt and touch one tank and the other and the other and the other and cross all the Earth probably and go to the space. But the tanks are receiving the information. And as the tank has also a GPS to determine the time, you can know if the shower is the same, which arrived the first tank, the second, the other, and produce a detection of several detectors, as you can see here in the blue light. If you detect on surface and also with the fluorescence detector, which detect the fluorescence in the atmosphere, your eye cannot see it, but the cameras in the Pierre Auger fluorescence detector can detect the fluorescence, you have an hybrid event. And underground, you have the scintillators of Amiga project there. This is the 3 kinds of detection of Pierre Auger for a moment, more than 3. We have 5 or 6 now, ways to detect the shower of secondary particles.
There is one question here.
Mm-hmm.
Have you, this is by Rutger Weiss, have you been able to identify events that can be assigned to a mother particle that has not yet triggered a complete shower? And what is the highest energy of a particle you have observed?
Well, Ricardo, can you answer this question?
Sorry, the first question?
The question
It's in the chat. It's in the chat, Ricardo.
Okay.
is if you have been able to identify events that can be assigned to a mother particle that has not yet triggered a complete shower. And what is the highest energy of a particle you have observed?
Well, I do not understand really the first one, but well.
I suppose that it means that if you have managed to catch a particle at the collision vertex or something.
Well, assign the to mother part.
Or before.
Well, about this, remember that we cannot see or detect the primary particle. We detect just the secondary particles shower. So the idea is to reconstruct the path in the atmosphere to determine the arrival point, and using the energy deposit in the water or in the scintillators, the detected energy, not the original particle, the cosmic ray, the primary cosmic ray energy, but the energy in the secondary particles, try to identify the particle, the original particle. So all that we maintain as event is connected with the particle, but the problem is, for a moment, we have not a good definition of the mass of this particle. We need to determine without any doubt which kind of particle, and seems to be a transition between low and high energy. It means at low energy that a part of the spectrum presented by Ricardo are protons, and highest energy seems to be iron. So we have to identify exactly which mass has the primary particle using all kind of detection. So the primary is not visible. We cannot detect. Remember, it's a proton, it's a nucleus. It's a nucleus of an atom. So it's not an easy particle to detect, but the showers produce interactions, and we detect the interactions. We detect light all the time. We detect fluorescence, and inside the tanks, we detect a kind of radiation called Cherenkov radiation. It's also in the ultraviolet region of the spectrum. So if we detect a shower, it's because more than one detector detect the front. It's like a front wave, but a front of particles. It's like a pancake or a membrane, which are developing through the atmosphere, made by particles. So the shower arrives, the tank detects the shower, other tank detect the shower, another, and you have at least 3 tanks. If you have at least 3 tanks detecting a front of particles, we call this an event. And with the energy, the measured energy, we determine the more or less the mass of the particle. And with the time of detection, we determine the core of the shower, of the whole area of the shower, and with this, the central part of the shower and the direction of arrival. And with the fluorescence is light also in the atmosphere, the interaction of the secondary particles with the nitrogen in the atmosphere. There is like a flash of light at some altitude, and this has energy also. So with this flash, we also determine the energy of the event, the primary, and the arrival. So using several different kind of detectors, we reconstruct the same phenomena. The secondary particle shower, the mass of the primary, the direction of arrival, the whole energy of this particle. And after that, we try to find the optical counterpart, which is the final object of this project, to find who or which kind of astrophysical source produce these high energy cosmic rays. About the energy, oh, sorry. Yes.
Sorry, please continue.
No, the last part, yes, Ricardo can say which is the maximum energy we detected.
Yeah, well, I do not remember exactly the detail, but it is few times 10 to 20 electron volts.
Yes.
That we
the highest energy.
Yes.
The highest. 10 to
20 by 20 by 10 to 21, if I remember, a few years ago.
Can I add something here?
Yeah.
If possible. Okay. So an old professor of mine used to say that particle detection is something like a necropsy, an autopsy. So the particle has passed, it has produced an effect, and we are measuring the effect in order to find out about the particle. This is actually what happens here, right?
Yes, exactly.
This is one thing. Now, if someone, regarding the question, the first part of the question, if someone was to take, let's say it's a Cherenkov telescope, it's a Cherenkov detector, and put it in the ISS. Okay, we have one. We have the AMS.
In the International Space Station. Well, there are some projects to detect cosmic rays from space.
Then we would be able maybe to observe the track of a very high energy nucleus passing through.
Yes, you can detect the particles, but probably well, yes, you can detect the particles and you can determine from where they come from and try to make some model. But remember that at this moment, we are combining observations. The idea is to combine observations. As we had one question about this, if you permit me to show something. This presentation, I will share the presentation with everybody. So don't worry, you will have the presentation available at somewhere where the organizers decide. But remember that we are in the time of the multi-wavelength because we use all kind of region of energies of the spectrum. It means the astronomers don't use anymore just the visible. We observe in ultraviolet, X-ray, gamma ray, infrared, radio, etc. We observe in all the energy regions of the spectrum. But now we also are talking about multi-messenger approach to the knowledge of the cosmos. Look at this image of our galaxy, the plane of the galaxy, observing in radio in different wavelengths. Not all the radio is the same. For example, 21 centimeters is neutral hydrogen. The hydrogen without, not ionized. Is the most part of the universe is hydrogen. But if you observe in 408 megahertz, it's another, the aspect of the galaxy, the plane of the galaxy. But look at the microwaves. This is the cosmic background radiation. And infrared is another vision. And here is the deep sky, if you want, is the galaxy invisible. And here you have the plane, and here the nucleus, the core of the galaxy. And here the Magellanic Clouds, the big and the small one. The Magellanic Clouds, galaxy, satellite galaxies from the local group. But if you observe in ultraviolet or X-ray, you will have another vision of the universe, completely different, because in each energy you have different kind of phenomena to detect. So, and look at gamma ray. Of course, the high energy, the extreme universe produce gamma rays. For example, a supernova explosion, you have gamma rays. But now we are talking about particles. And look, this image of the same object, a map of the galaxy. You cannot see the plane, but you see spots. And these are regions from where our events, the events of the cosmic rays, are coming from. They are objects, perhaps objects, the most part not still knowing. We don't know exactly from which object the events are coming from, but there are some objects very well known which produce cosmic rays. Thus, the galaxy, the Centaurus A in English, which is a very, very well-known galaxy which produce cosmic rays of high energy. And look at this. This is the same map with another very important result from Pierre Auger Observatory, which is the discovery of the extragalactic origin of the cosmic rays, because here you see there are two colors. Well, here the pink color represents an excess of cosmic rays. It means there are cosmic rays arriving from outside the galactic plane, outside our galaxy. And here I would like to show this because during a meeting of the Argentinian Association of Astronomy, at the same meeting, we had the luck to have two presenters. One from Pierre Auger, Esteban Roulet from Balseiro in Bariloche, and here is Gabriela González from LIGO. And in the same meeting, Gabriela talked about the recent detection of LIGO, of gravitational waves, and Esteban was showing our discovery about the extragalactic origin of cosmic rays. But in the same year, probably you remember this news. This was a news about the collision, the merge of two neutron stars, which were discovered on August 17 in 2017 at an exact time. Discovery using the gravitational waves facilities on Earth, the two instruments at the United States and one at Europe. And was the first messenger arriving on Earth. Less than 2 seconds late, a satellite, a gamma ray satellite, Fermi, from NASA, records the gamma ray burst, the second messenger from this merging, this fusion of neutron stars. And some time later, the telescopes detected the light. The photons were the last messenger here. And the telescope followed the collision. And as you can see, the colors of this merge change from blue to red. And during these days, chemical elements appear in the spectrum of the fusion, of this collision of neutron stars. And with all the data, we can reconstruct the arrival direction and determine exactly the location, the place, the site in the universe, which was an object, NGC 4993, at 130 million light years from Earth. And this also, according to the theory and others observations, produce neutrinos. If you have the right instrument in the right place to detect neutrinos from this collision, according to the theory, the direction is this point line in yellow, you can detect if in this event were neutrinos. Who was in the right position, permitting me to put a human characteristics to the observatory, Pierre Auger. And Pierre Auger started at the same time of the detection, the study of all the observation, tried to determine if the neutrinos were produced, and the answer was negative. No neutrinos were detected for this fusion. And all this research from instruments in space, gravitational wave detectors, neutrino detectors, light detectors, started or were the beginning of the new era in the science, the era of the multi-messenger detection. So we are really happy to be part of this time in the history of the humanity in which we are able to use all our brain to make these incredible discoveries.
So I think that maybe this would be a good moment to stop for today. We would like to thank you all very much for this extraordinary experience you offered us. We have many questions also. You see right now in the Facebook live event, there is a discussion taking place about energy measurement for cosmic rays, and it's beautiful.
Remember that these cosmic rays are not dangerous for the people at all. The energy arrived to the surface of Earth very, very diluted. So it's high energy in a tiny particle, but it's not a high energy for our bodies, for example. It's not like X-ray experience at the hospital, no, at all. The energy is high for a proton or a nuclei, but it's not a compromise for the health. Now we are crossing by a lot of particles without any effect in our body, okay? I don't know if the people in Pierre Auger are there. Please turn the cameras on because you must say goodbye. And thank you very much, the organizers. We always live a very exciting experience with the people and showing our instrument, our observatory, this apparatus, as James Cronin said. Remember that James Cronin, one of the fathers of Pierre Auger, was Nobel Prize in 1980 and was part of this adventure. Now he died, but we always, each day, remember his figure.
So,
Okay.
thank you.
Thank you, all of you. We are very happy to have this talk with you. I hope that you understood us, and it was a very good experience for us.
Thank you.
Yes, thank you. Nice, very nice. Thank you.
Thank you, Mariana.
Let me just say that the recording of the presentation will be for the participants in the Indigo page, and for everyone who wishes to see it again, it is in the chat, it is in the Frontiers Facebook page, where everything is there, okay, from the live event. So again, Beatriz, everyone, thank you very, very much for this opportunity.
Now, thank you for the invitation, and you are welcome to visit again the observatory when you want.
Thank you, thank you, thank you, thank you. Bye-bye.
Thank you, guys.
Bye-bye.
Bye.
And
Bye.
girls, bye.
Bye bye.